So I am representing RISE, and in particular, I'm representing one of the many projects that we have in collaboration with the Swedish Space Agency and AI Sweden. We have been working in this space for quite a while, and I'm talking about the innovation space of Sweden. The National Swedish Space Agency is interested in funding projects and helping initiatives that strive to improve the use and usability, I would say, of space data in general in Sweden. And this is one such initiative that, as was introduced, is running in the third iteration. I'll be speaking about one key component of this innovation system, which is Digital Earth Sweden. This is a digital platform for exposing Earth observation data, in particular satellite data, to Sweden. And we're using this as a source in our larger innovation platform, which is the Space Data Lab, which focuses on the collaborative aspects. This was a Vinnova-funded project on digitalization. So I will be talking about data and the particular data sources that we're using, the problems that people have with this data, and also what we're offering in terms of solutions to them. I'm showing here an image of many of the different satellites that have been launched since we found it. I mean, if we go back a bit in time, the satellite industry was really a technology that was initially military technology that found vast civilian applications. But the problem with using satellite data, Earth observation data in general, but in particular satellite data, is that there are many, many different satellites. Just within Europe, we have 3 large programs that have hosted and launched a number of satellites successfully, where some of them are perhaps more well known, and then I'm talking about the Copernicus program satellites. I'm not sure how many in the audience are familiar with any of these terms of these satellites, but I want to tell you that there is a wealth of them, and they are all providing very rich data sources. But there are many of them, and on each satellite, there are even more instruments. So we have many instruments, many satellites, and each instrument provides many different data formats, and they are all distributed through a ground segment that has many different distribution channels available. This is a jungle to operate in and to get introduced to as well. Even if you are a GIS, I mean a global information systems expert, there is still the data engineering challenge of just locating and understanding all of these data formats. And this is a challenge that we have taken upon ourselves at RISE to work with. In particular, because companies and authorities, they typically hire GIS experts, and none of them are really interested in developing and hosting these systems that process, gather, and index and expose all of these data sources in a secure way. So what what does this data look like? I'm going to give you some examples. This is a very deep topic, I think, and it's always a struggle to give a short presentation. So I'll try to be compact and still give you some ideas on both, like what the data is and what technologies that we are using, because I think it's important to talk about the actual stuff that we do. This is a Sentinel-1 set of data, so it doesn't correspond really to what we typically expect out of a forest, in that it's not. I mean, the forest on the ground is not green, obviously. This is radar data over the Ever Given incident in the Suez Canal, and I think it's interesting just comparing 2 data sets from 2 different times. You can clearly see what incident we're looking at. If you follow the canal up to the north, you can even see the Ever Given being lodged in the Suez Canal and the vast amounts of accumulating ships in the Gulf of Suez. All of these give off different radar signals, which are clearly identified. And I think it's an interesting show of the resolution and the quality of the data that is seen from the Sentinel-1 satellite. So this is radar data. This is a radar signal that is sent down to the Earth and then bounces back up to the satellite. And then the difference between the emitted and the received signal is what can be used to derive these kinds of data products. Then There are also data products like Sentinel-2, and this more or less corresponds to what you would imagine if you were to tape a point-and-shoot camera and launch it into space or into orbit, looking down on the planet, if you will. This is the Cumbre Vieja eruption during, I think it was 2021. I'm not sure exactly the date, but what I think is interesting here is that we're seeing, if we pause for a minute and think about what we're seeing, this is an image that has been corrected both for the geometry of the underlying landscape and also for the atmosphere and all of the interferences that come from the atmosphere. The atmosphere is a huge stack of different, that contains all kinds of different matter that impacts the radiation that is observed by the satellite. But the Sentinel-2 product contains both this RGB image and also infrared image, so we can very clearly see this large lava flow entering from the volcano out into the ocean. And this is a piece of data from Sentinel-3, and Sentinel-3 typically provides us a number of data products related to heat or to temperature, both of the land and of the sea, which is something that is becoming more and more interesting to use as a piece of data to train various models, and this is shown in Europe, of course, in a heat map. So while all of these satellites have global coverage, what we are focusing on is really providing the highest resolution possible data over Sweden, and this is roughly the area that we're focusing on. And what happens if we follow the data all the way from the satellite to the actual end users is that the satellites they revolve about the planet and monitor the surface, and then this relevant data is automatically discovered and downloaded by our systems from endpoints provided by ESA. And we then perform pre-processing of the data. It is then indexed and made searchable in our databases, and the data is then exposed through open and unified APIs. We're doing this to enable machine learning for this, based on this data, and we're building it all on open source technology from the ground up, which I think is an important piece. And it's also a prerequisite for applying for a lot of the funds that we work with typically. This runs it's container-based and runs on Kubernetes, and it is also hosted at a local data center, and I'll get back to that in a short while. And typically what people want to do, the problems that they want to have solved, is that they want to look at a specific time series. Say they have specific dates when they want to view a certain data source. And here I'm talking about the actual query that they're forming, the prompt that they're forming and providing to these systems. We want to look at a time series of images or a time series of data sets, and the systems should be able to adapt to this. They might also want to be able to look at just a small geographic area or a specific polygon, typically, within this data set. And many of these data packets that are provided by the European endpoints, I mean, each product is large. They can be everything from 50 to 300 megabytes in size once you unpack them. And needless to say, if you want to look at a time series of hundreds or thousands potentially of different pieces of data, then it becomes completely unmanageable in terms of I/O, because you have to download lots and lots of data. You will be really hammering the endpoints and the servers that provide them. And in the end, what you want to do is to cut out this little piece of data out of the whole to look for something certain, and for some certain area. And it really, I think it's interesting in the general sense, this working with Earth observation data, is that this is typically the case for all use cases, that you have this massive amount, we have this massive amount of data collected about our planet, but when we want to answer questions, we are really looking at a small sample or a small piece of that data. And there is also, I mean, I think one of the big challenges here really is that we have collected more data in the last few years about our planet than we have throughout the history of humanity. But we really haven't stepped up our processing capabilities to the same levels, and that is why you see a lot of these calls being put forward by the EU to really stimulate innovation in this area. So a bit on the technical side is that we are using a piece of infrastructure called Open Data Cube. This is one of the open source tools that we're using. And it was originally funded by the Open Source Geospatial Foundation. It was a project through that fund. And based off of this piece of technology, a number of these different innovation hubs have popped up across the globe. You have the Swiss Data Cube, you have the Australian Geoscience Data Cube, and all of them are different innovation platforms that focus on with different goals, of course, focus on fostering collaboration in these areas. But it's really enabled. It's enabled by these core pieces of technology that are open source. And all of them are built on Open Data Cube. And what Open Data Cube does is that it helps you organize data from various satellites. And it's built like it's built on top of Postgres, and it provides a bunch of endpoints through Python that allows us to really query the data, not just on a product basis, saying that I want to look at this gigantic piece of heavy data, but only a small subset. And it is connected to existing GIS software as well. So it's a really interesting piece of technology that solves the indexing problem of this data, because the data itself is you get a zip archive, and with that comes like a piece of metadata that is really rich, and you have a bunch of data points, and you want to search that somehow, right? So you need an indexing engine to be able to at all sift through all of this metadata. And this is something I'll talk more about during the provocation sessions, how we can at all search through all of this data and make sense of it. So I welcome you to listen in tomorrow. We expose an Explorer interface that allows you to look at what data we have available over, all the extent of time for each different product, which is a rich way of kind of engaging with this data and browsing it. We also expose a bunch of different open web service endpoints, and these are ways for us to mirror data that is available from Lantmäteriet in Sweden. So you can take data from us as just an endpoint and take the endpoint and put it inside the GIS software and import data that way. Another key piece is OpenEO. This was output also by a Horizon 2020 research and innovation project. It is also open source, and it provides a web API through which you can access stuff that we store via Open Data Cube. So it's a layer between Open Data Cube that allows us to do a lot of different interesting analysis. It supports batch jobs, so we can send in batch processing jobs, which is a key piece, I think. It also has a REST API, so we can query it using standard format. We can put up these notebooks, and I encourage you, everyone who listens in and thinks this sounds interesting, I think you should visit our GitHub repository where we host all of these different notebooks. All of them are focused on using our platform in some way for a specific purpose, and they are very verbose, I think. They do not assume a lot of knowledge pre-hand. So they cover everything from using the system just to retrieve a piece of data to actually calculating the difference in time between two pieces of data. And this is anyone can access this, just to go in and be inspired by the different Jupyter notebooks that we have deployed. And the team has worked great. Our development team has put in lots of hours putting together these notebooks. So I really encourage you to take a look. And also, if you feel like this sounds interesting and you want to try something on your own computer when you get home, then contact me personally, and we can set up a user for you so that you can poke around and try to retrieve some data. So if we follow this idea of the user interacting with the system, going from the left, the user is exposed to a bunch of different endpoints. You have these VMS services, which I talked about. You have tools for indexing, you have a data cube, you have OpenEO that provides these rich API endpoints that you can connect to. And all of this is handled via authentication using common authentication services that are deployed elsewhere. And then on our side, we have all of these different backend services that communicate with an automated system that discovers and downloads new products all the time. So our systems are always running, looking for different new products for different satellites that we've registered. And depending on the people that we work with, we set up different downloading processes. But all of this is automated, which I think is interesting. And it is also available from one location, all of the data. And practically, when we want to include a new piece of data, we on the left side we have the satellites that are connected to some endpoint. They have products that they expose through some endpoint. This could be EUMETSAT, it could be the US ground segment endpoints, it could be Google Cloud Storage. And then on our side, we provide abstractions or providers for these different endpoints that our system can then discover and download products from. I won't go too deep into this because it gets a bit technical quickly. We also use GitOps for all of this, if that means anything to any one of you, and it's all managed via Argo CD. So we have version tracking of the entire system, and every time we make an update, we have this continuous delivery system that pushes out new deployments. So it's a really comprehensive and quite complex system, actually, in the end. So it supports traceability and rollback of versions and so on. And I think it's also one unique selling point for us, or selling point, if I should call it that way, is that it's also hosted locally. As a bit of a reflection, this idea of sovereign control of data is something that has really popped up in the last few years. I think with the war in Ukraine and all other worrisome conflicts in Europe, the idea of sovereign control of data is really something that has started growing. And we were early on the ball, so to speak. ICE data center is a data center that is built a few hundred meters away from my office. I actually built, I was in this server hall of building the infrastructure for our cluster. So we have tight control over where the data is hosted and who has access to it. And I think that's powerful in its own right. So that is the core of the Space Data Lab in Sweden, the result of many years of collaboration with many authorities in Sweden, companies as well, of course, mainly the Swedish Space Agency, which we are very tightly coupled with through these projects, AI Sweden and so forth. So I suggest you visit this webpage that we have worked on putting together. And also you can, if you have any questions, if this sounds interesting, if you want to know more, you can contact me personally on this email and I'll respond as quickly as I can. And that is all from me.
Thank you so much, Erik.